The reliability of electronic products is becoming more important every day. International competition demands quality and reliability at the lowest possible cost. At the same time, there are significant changes within the electronics assembly industry to reduce solder joint touch-up and rework. We normally think of touch-up and rework as adding to the overall quality of an assembly, since we're fixing or improving solder joints that are less than perfect. But that's where these changes come in. Current revisions to the industry workmanship standards have actually relaxed or eliminated some rework requirements in order to improve quality. This is a potentially confusing change that merits a thorough explanation. The ANSI J Standard 001 and the IPC A610 are industry specifications that many companies in the electronics industry use for workmanship standards. In the past, these specifications defined acceptance criteria using the terms preferred, acceptable, and rejectable. But the unspoken emphasis was always to obtain the preferred condition. Even when a solder joint was considered minimally acceptable, it was often reworked to achieve the preferred status. In some cases, this may have happened because people took the term preferred too literally, or because they really wanted their products to be the best they could possibly be. In the current revisions of these industry standards, these terms have been changed to target condition, acceptable, and non-conforming. The obvious difference is the change from preferred to target condition. But there has also been an important change in the definition for acceptable conditions. The term acceptable is now being defined to mean two specific things. First, if a solder joint meets the minimum acceptable conditions, it should be left alone. And second, if a solder joint meets the minimum acceptance criteria but exhibits certain cosmetic imperfections that are not detrimental to the reliability of the solder joint, these types of conditions now fall into a new category called non-conforming process indicators. The idea here is that the process that created these imperfections should be changed, rather than the cosmetic imperfection. This makes a lot of sense, since when you fix the process, the incidence of imperfections will be reduced or eliminated. These cosmetic imperfections include certain types of voids, pinholes, and other surface irregularities that are not considered to be harmful to the reliability of the solder connections. This reduction of unnecessary rework has several advantages. First, it saves time, but it can also have a beneficial effect on the overall reliability of the assembly. To understand how this works, we'll need to look inside a plated through hole to understand what happens to the structure of the materials whenever heat is applied. Let's begin by reviewing how the plated through holes were originally created. After the holes are drilled in the circuit board, the walls of the holes are plated with copper to create an electrical connection between both sides of the board and any internal layers of circuitry that may exist. The copper is often overplated with tin or tin lead during the same electroplating operation. Eventually, the component leads will be inserted into these plated through holes and soldered either by hand in the wave soldering machine or in a solder reflow process. The heat of the soldering operation is pretty intense. In fact, it's hot enough to cause the laminate material to expand quite a bit in thickness. Every material reacts to heat differently and will also expand at different rates. There's actually a numerical index that exists called the coefficient of thermal expansion, which measures how much a specific material will expand when it's heated. Notice the difference between these numbers for a typical epoxy laminate material and the copper plating on the walls of a plated through hole. What this means is that epoxy laminate will expand much faster than the copper during solder rework. When the laminate grows, the copper can actually crack if it's not soft or ductile enough to absorb the expansion. And most rework operations will require two heating cycles, one to remove and another to replace the solder. That's two extra chances to create internal cracks in the plated through holes. On multilayer boards that have internal connections to the interlayer circuitry, even a small crack can cause an electrical open or intermittent failure. This type of internal damage will not even be visible to the rework technician. Also keep in mind that the laminate will also expand and shrink to a lesser degree whenever an electronic product is turned on and off. This can aggravate a small crack that might not show up during electrical test into an eventual failure out in the field. And that translates in any language into unhappy customers. The point of all this is to explain why it's very important to avoid unnecessary rework. The attempt to obtain cosmetic perfection in the past may have actually decreased the quality and reliability of some interconnections. The acceptance of a solder connection should always be based on the requirements of your company's workmanship standards, and not on any individual's personal expectations. If you would like a detailed explanation of the acceptance criteria for through-hole solder joints, including process indicators, you can review the IPC video on through-hole solder joint evaluation. The remainder of this program will concentrate on the tools and rework techniques for many of the common defects found on through-hole assemblies. But let's pause first to discuss any questions you have on the information we just covered. In this next section, we're going to examine the common tools and materials used during through-hole rework. Let's begin with the hand soldering iron. There are a variety of temperature-controlled soldering irons, maybe even within your own company. Perhaps the most important thing to remember is to always keep the temperature at a safe, controllable level during any type of rework operation. 315 degrees Celsius or 600 degrees Fahrenheit is a reasonable starting temperature for most hand soldering operations. Cleaning and tinning the tip of your soldering iron is equally important for proper heat transfer and tip life. Always remember to wipe the tip on a clean, damp sponge, and then apply a light coating of solder before you begin any rework operations. Now let's talk about soldering flux. Flux is an essential ingredient in the soldering process. Its purpose is to remove oxidation, which can prevent proper wetting or bonding of the solder. It's also helpful in transferring heat between the tip of the iron and the component lead and land. You'll find that any solder joint will melt faster if there is a coating of flux to help transfer the heat. You could also think of it like a frying pan. If you were to quickly touch your fingers to a hot frying pan, you might feel the sensation of heat. But if that pan had a coating of hot oil on it, you would probably burn your fingers. Don't try this heat transfer experiment at home, please. The importance of efficient heat transfer is worth a little more discussion at this point. If you think of time plus temperature as the total amount of applied heat, then when you reduce either one of these variables, you have applied less total heat. And remember that the less heat you apply, the less likely you are to damage the circuit board. Of course, there are many other factors that can affect the rate of heat transfer, which always need to be considered. There are also many different types of fluxes available. Some are very strong or active, and some are relatively weak or mildly activated. Strong or highly active fluxes can be severely corrosive to metal unless they are removed after the soldering process. This cleaning process may require certain chemicals or solvents that create problems in our environment. Some companies are changing to less active fluxes that may not require cleaning after the soldering process. These are sometimes referred to as low residue or no clean fluxes. Your soldering process may require slight modifications in order for these low residue fluxes to work properly. If you would like more information on hand soldering with low residue fluxes, you may want to review the IPC training video on this subject. In any case, your company will decide which type of flux you'll be using. It should always be compatible with the flux used during the wave soldering operation. The next rework material is solder braid. Solder braid comes in various sizes or widths for various solder removal operations. The braid is made up of copper strands with a powdered or dried flux inside. When the braid is heated by the soldering iron tip, the molten solder will be drawn up into the copper strands. Once again, your company will supply you with a solder braid that's compatible with your soldering and cleaning processes. The final tool we'll be using is the vacuum extractor. This tool has a heated tip with a hollow orifice or hole in the center. Attached to the back of the tool is a flexible hose which vacuums the liquid solder into the storage chamber inside the tool. There are also various tip sizes and shapes for different solder removal operations. We'll be discussing proper tip selection as we review specific rework procedures. Both the tips and the storage chamber will require periodic maintenance as defined by the tool manufacturer or your company's standard operating procedures. It's important to perform this preventive maintenance in order to consistently obtain the best results. Obviously, you will need to empty the solder from the storage chamber before the tool becomes clogged, and be sure to always deposit the solder in the proper receptacle. Now let's take another break to see if you have any questions on the tools and materials you'll be using before we describe the first rework technique. In this next section, we'll be discussing the vacuum extraction process for removing round-leaded components. Let's start with the unclinched or straight-through leads. Axial leaded components have round leads, extending out from either side of the component body. They come in various sizes and shapes. Radial leaded components have round leads, extending from the bottom of the component. They also come in various sizes and types. Now let's talk about tip selection for desoldering round-leaded components. On the solder side of the board, you should be able to see the outline or shape of the component lead inside the solder fillet. The width of the vacuum tip should be approximately the same as the land, and the hole in the center of the tip should be slightly larger than the diameter of the component lead. This will allow the molten solder to flow past the lead into the solder storage chamber. Now insert the selected tip into the tool and tighten the set screw. Once again, our general starting point is 315 degrees C or 600 degrees F. This should be sufficient for most vacuum extraction operations. It's also cool enough that it won't burn the surface of the board if you happen to touch it by accident. We do have the option to apply a small amount of flux onto the joints to be desoldered. There are a variety of different ways to apply flux. Remember that the purpose of this flux application is to speed up the heat transfer between the desoldering tip and the solder joint. Some companies prefer not to use flux to avoid cleaning the assembly after the rework operation. Always make sure to follow your company's recommended procedures for flux application and cleaning. Now we're ready to position the board for the desoldering operation. You can clamp the assembly in an upright or vertical position in order to view both sides of the board at the same time. Although most people prefer to work with the board secured in a flat or horizontal position. Now we should be ready to begin the vacuum desoldering operation. When you apply heat onto the first connection, the solder should melt rather quickly. At that point, you'll feel the tip drop down onto the land. Now move the lead around in a circle without applying pressure onto the land. As the solder melts, the lead will move more freely. Upon complete solder melt, press the vacuum switch to draw the molten solder up into the handpiece. After the solder is removed, continue to move the lead around in a circle with the vacuum still on. The fast-moving air will now cool the metals inside the hole. This will also make sure that the liquid solder is drawn all the way into the vacuum chamber rather than stopping inside the tip. After 1 or 2 seconds, you can remove the tip, then stop the vacuum. The component lead will probably lean back against the edge of the hole wall. There may be a few small beads of residual solder inside the hole. If we didn't cool this residual solder with fast-moving air, the lead could now reattach itself to the side of the hole. This is called a sweat joint. If you try to pull a sweated lead out of the hole, this could potentially rip some of the metal right off the hole wall, and a damaged hole wall can be difficult to repair. Now we're ready to desolder the remaining leads. Let's do it in real time to demonstrate the proper sequence and timing of the operation. First, we apply heat. Feel the tip drop down. Move the lead around. Activate the vacuum. remove the tip, and stop the vacuum. The component should now be ready to remove. It should offer no resistance at all. Whenever a component won't come out of the holes without resistance, you'll need to determine which lead is still attached to the hole wall. You can do this by attempting to move each lead with a holding tool. If one or both of the leads are stuck, you won't be able to move it freely. In this case, we'll need to add fresh solder to the hole. It's always a good idea to allow the area to cool between each heat application. This can help prevent damage to the laminate surface, lifted lands, and cracks in the plated through holes. After the solder cools, repeat the desoldering operation until we obtain a sweat-free joint. Let's stop and make sure that you understand the basic operation of the vacuum extractor for the round-leaded component removal process. In this next section, we're going to discuss the removal of clinched leads using the vacuum extractor. Some component leads are bent over or clinched during the automatic insertion process. This is done to hold the component in place prior to wave soldering. There are various degrees of clinching, ranging from partially clenched to fully clenched. You can easily spot a clinched lead, since the outline of the lead should always be visible underneath the solder. There are several techniques for desoldering clinched leads. Let's begin with the partially clenched lead. We'll need to bend the lead upright before we can desolder the entire joint properly. The vacuum extractor tip can be used whenever the lead is not clinched completely flat against the land. Again, you may want to start by applying flux to help speed up the heat transfer process. Tip selection will be the same as before. We'll place the vacuum tip parallel to the clinched lead, right at the end of the lead. As the solder melts, slide the tip forward until the lead is completely inside the tip. Now, bend the lead upright. The component lead and the molten solder should now transfer heat all the way through the hole. Move the lead around in a circular motion, then activate the vacuum. After you remove the tool, continue the vacuum for a few additional seconds. The entire operation should now be repeated on the second lead. This method will work for most partially clinched leads. On fully clinched leads, you may have a problem getting the tip of the desoldering tool underneath or around the lead without damaging the land or the board. There are 3 alternate techniques for desoldering fully clinched leads. The first method uses a thermal parting tool with a flat end tip. The tip of the parting tool can be used to melt the solder and then bend the lead upwards. After the lead is straightened, the vacuum desoldering tool will desolder the connection. Let's look at this lead straightening process in more detail. The heat setting for the thermal parting tool should be specified by the manufacturer or your company's standard operating procedures. We always start by setting the correct temperature on the power supply. Then we position the tip against the end of the clinched lead. Next, we activate the heat, typically with a foot pedal. The heat should ramp up within a few seconds and begin to melt the solder. When the solder melts, we'll start to lift. At this point, you should be able to bend the lead straight up. It's a good idea to unclinch the other lead at the same time, so you aren't constantly shifting tools back and forth. After the second lead is straightened, place the thermal parting tool back in the tool holder. The solder shouldn't stick to the tip, so there's no need to clean it. You can also use a chisel tip on a hand soldering iron to perform the same unclinching process. We begin by selecting a small double-sided chisel tip. Again, we have the option of adding flux. Then we position the tip at the end of the lead. Once the solder melts, push the lead straight up. You need to be careful not to wedge the tip down into the board during this process. This can gouge the board or lift the land along with the lead. After we've properly unclinched the second lead, we're ready to desolder both of the joints with the vacuum extractor, just like we did before. The third technique uses the vacuum extractor and pliers to straighten a fully clinched lead. We begin this process by placing the tip of the vacuum desoldering tool against the junction of the lead and the land. When the solder melts, activate the vacuum. At the moment, we're only trying to remove the solder that connects the clinched lead to the land. There may be a slight solder bridge remaining between the land and the lead after this desoldering process. If this bridge is relatively small, we'll take a flat-nosed pliers and gently twist the lead to one side. You should be able to feel when the lead is completely free from the land. Then bend the lead upright in preparation for the vacuum desoldering operation. At this point, you'll need to decide if there's enough solder remaining inside the hole to transfer the heat properly. If the remaining solder fills the hole up to the top of the barrel, you can usually desolder the connection as is. But if some of the solder in the barrel was removed during the unclinching process, it may be necessary to add additional solder to the joint. This extra solder will help ensure proper heat transfer during the vacuum desoldering operation. After the connection has cooled, we apply the heat. Feel the tip drop, move the lead around, activate the vacuum, remove the tool, and stop the vacuum. That should cover the vacuum desoldering process for partial and fully clinched round-leaded components. Let's take another break to make sure you understand all these processes before we discuss flat-leaded component removal. In this next section, we're going to be removing dual inline packages with the vacuum extractor. Notice that these dip components have 2 rows of flat leads. Each of these leads will have either a tapered or flat shoulder. This is designed to hold the component away from the surface of the board for cleaning purposes. For flat leads, the vacuum tip needs to be sized so that the width of the component lead will fit inside the desoldering tip. And like before, the tip should not hang over the edge of the land whenever possible. We can perform an optional flux application onto the leads on the solder side of the board. And positioning of the board will be based on your personal preference. We're ready to start at one of the corners. You'll often find that 2 of the corner leads will be partially clinched to hold the dip in place prior to soldering. Typically, these partial clinches can be desoldered with the vacuum extractor. Starting on the clinched corner lead, we'll angle the vacuum tip parallel to the lead, then push the lead inside the tip as the solder melts. When the solder joint is molten, we can bend the lead upright and position the tip squarely onto the land. After the entire joint is melted, we'll move these leads back and forth rather than around in a circle. Then activate the vacuum and continue drawing air through the hole to cool any residual solder. After we remove the tip, continue the vacuum in order to draw the solder all the way into the storage chamber. In order to avoid potential heat damage to the board, we'll need to skip around rather than desolder in a continuous line. Some people prefer to desolder the corners first, then they proceed to alternate back and forth in this same pattern. Others simply skip every other joint and work their way around twice until the job is completed. Either way, keep repeating the operation until all of the joints are desoldered. Hopefully the component should come out of the board without any difficulty. Remember never to pull it with any force. If it doesn't come out easily, you'll need to figure out which leads have sweat joints. You can do this by gently moving each lead until you find the one that doesn't move back and forth. Then we'll add solder to this particular joint in order to transfer heat all the way through the hole. Always give the joint a few seconds to cool off after you add solder to avoid overheating the hole. Now you can desolder the hole again and the dip should be ready to come out. That covers the removal process for dips and other flat-leaded components like D-packs or power transistors. In this next section, we're going to be discussing some of the auxiliary heat techniques you might need to desolder components on large thermal mass or multi-layer boards. Whenever you find that you're having trouble melting the solder all the way through to the other side of the hole, you might find it advantageous to use an auxiliary heat source on the opposite side of the board. There are several options. depending on the tools you have available. One method is to apply a resistance tweezers on the component side of the board. Be sure to use the recommended heat settings specified by the tool manufacturer. After you activate the auxiliary heat on the component side, wait a few seconds. Then apply heat to the solder side with the vacuum extractor. When the solder has melted all the way through the hole, apply the vacuum. You can also use a standard hand soldering iron as an auxiliary heat source. This takes a little more dexterity since you'll need to be able to work with both hands at the same time. The addition of external flux onto both sides of the board can also help improve the heat transfer. Again, this is optional depending on your company policy. We begin by preparing the tip of the soldering iron. Remember that a cleaned and properly tinned tip will transfer heat much faster than an oxidized tip. Position the soldering iron tip on the component side of the board against the lead in the land. Now place the vacuum tip on the solder side and wait until you feel it drop down onto the land. Then start to move the lead around and activate the vacuum. Withdraw the soldering iron and continue the vacuum until any residual solder in the hole has cooled down. Then remove the desoldering tool and continue the vacuum for a few additional seconds to make sure that all of the solder reaches the storage chamber. Continue this same process until all of the leads have been desoldered. Remember to skip leads on multi-leaded components and to move flat leads sideways. Round leads are always moved in a circle. These auxiliary heating techniques can be useful in a variety of situations. Just keep in mind that you are applying a lot of heat, so don't overdo it. It is possible to damage the board if you keep the heat applied for too long. Another technique that can be helpful when you can't access the leads on the component side of the board or during multi-layer rework is to preheat the assembly prior to the rework operation. This can be done in a convection oven or on specially designed local area preheaters. It can take a few minutes to bring the temperature up to 100 degrees C, but preheating does have some distinct benefits. First, it reduces the amount of direct heat required to melt the entire solder joint. This can reduce the chance of potential damage to the board. Preheating can be advantageous prior to many types of through-hole rework, but it does take time and specialized equipment. Your company policy on preheating will decide when to utilize a preheating process. Let's stop now and discuss the specific sources and situations where auxiliary heat may be useful in your work. In this section, we're going to show you how to fix solder bridges and icicles, as well as insufficient and excessive solder conditions. Remember that we never want to fix any solder joints that meet the minimum acceptance standards. Let's start with the condition that always needs to be corrected: solder bridges. Some of the smaller solder bridges can be removed with the tip of the soldering iron. Chisel tips are usually preferred over conical tips since they have more surface area to draw or wick the excess solder onto. We will need to use flux for this particular operation. If you've ever tried to reheat a solder joint without the aid of flux, you'll understand why flux is required. The flux should be applied onto all of the affected joints and over the solder bridge. Next, we'll select a chisel tip for the soldering iron, and prepare the tip by wiping it on a damp sponge to shock off any oxidation. Place the clean tip on the solder bridge and reheat both joints completely. As you draw the tip away from the joint, the excess solder should flow toward the heat source. If you don't reflow both of the joints completely, you take the chance of weakening the internal structure of the solder. It's kind of like melting wax onto a candle. The strength or bond of the freshly melted wax will never be as strong as the original candle. In this situation, you will need to go back and reflux the partially melted connection. Then reflow the joint completely. Another process for bridge removal uses solder braid. We begin by selecting the braid width for the particular bridge we need to remove. We'll be holding the braid across the solder bridge like this. correct width of the solder braid is important. If the braid is too small, it can take several heat applications to remove the solder. If the braid is too wide, it may overhang the land and burn the surface of the board. Now we install a chisel tip and make sure the temperature is set to 315 degrees C. A chisel tip will usually transfer the heat much faster than a conical tip. The optional addition of external flux onto the solder braid can also help speed up the heat transfer. Place the solder braid over the first joint, then apply the heat. When you see the solder stop wicking up into the braid, remove the braid and the tip at the same time. Now we'll reposition a clean section of the braid over the second joint and touch it with the tip. When you see the solder stop wicking into the braid, the operation is complete. We'll need to give these joints a few seconds to cool down. This time can also be used to trim the used portion of the solder braid. Now we're ready to add some fresh solder to the joints that we just desoldered. There should be enough flux in the core of the solder wire to reflow the entire joint properly. But we do have the option of adding flux if necessary. To resolder the joint, place the tip of the iron against the intersection of the lead and the land. Then touch the tip of the solder wire to this junction to start the flow of solder. Now move the solder wire over to the other side of the joint and remove it when you have formed a proper fillet. If you have any questions about proper soldering techniques, you can review the IPC videotape on hand soldering procedures. It's also possible to remove solder bridges with a vacuum extractor. We'll essentially be removing as much solder as possible from the joints that are bridged, then we'll replace it with fresh solder. We have the option of adding flux to help improve the heat transfer. Remember that rapid controlled heating is the goal. On straight-through leads, always start on top of the lead, just like you were removing a component. Try to get as much solder out of the hole as possible. The excess solder from the bridge should also be attracted to the heat source. Repeat the same desoldering operation on the next joint, and remember to give both connections a few seconds to cool down before resoldering. If the bridge leads are clinched, place the extractor tip in contact with the lead and the land until all the solder melts. Now vacuum away as much solder as possible from the first connection. Then move the vacuum tip over to the second land at the junction of the land and the clinched lead, and repeat the desoldering operation. It isn't necessary to straighten the clinched leads for this particular rework operation. That covers the removal of solder bridges using all of the different techniques. You'll need to decide which technique to use for specific situations. Now let's talk about solder icicles. In some cases, icicles may be acceptable depending on their location, size, and the type of product being built. Remember that whenever possible, it's always best to leave solder joints alone. Having said that, there are some cases where icicles will need to be removed. The easiest way is to use a hand soldering iron and a bit of flux. We always begin by preparing the soldering iron tip. Then we add a little bit of flux onto the joint. Now we apply the heat and reflow the entire solder connection. As we pull the tip away from the joint, the excess solder should follow the heat source. The resulting solder joint should meet all of the workmanship standards for acceptability. You can also use solder braid or a vacuum extractor to remove icicles. In both cases, we'll be trying to remove as much of the original solder from the joint as possible. Then we'll add fresh solder to create the proper fillet shape. Both of these operations will take longer than a hand soldering iron and require 2 heating processes. For this reason, it makes more sense to use a hand soldering iron for icicle removal whenever possible. Now let's talk about reworking solder joints that have excess solder. After you have determined that the connection does not meet your company's workmanship standards, you'll need to decide how to remove the solder. The simplest and fastest method is to add flux. Prepare the tip of your hand soldering iron. Then reflow the entire joint completely and remove the excess solder with the tip of the soldering iron. You can usually remove enough solder from the joint on the first try. Even if you have to perform this operation twice, it still takes the same amount of heat to remove the solder with solder braid or a vacuum extractor, and then replace it with a hand soldering iron. Another condition that may require rework is insufficient solder. After you have determined that the solder joint does not meet workmanship standards, the simplest fix is to heat up the entire joint with a hand soldering iron. Then add enough solder to create a proper fillet. The flux inside the solder wire should be sufficient to reflow the existing solder all the way through the hole. And finally, you may run across different kinds of surface imperfections that may have required rework in the past. As we discussed at the beginning of this program, these may now be classified as process indicators. We want to be very careful not to rework any solder joints that fall into this category. Through-hole rework requires educated decisions. There are a number of factors to consider for each different situation. If you ever have a question, don't just reheat or replace the solder. Ask your supervisor. Asking shows that you care about what you do. Knowing when to rework is just as important as using the proper techniques in order to do each job properly and safely. Now let's review the information we covered in this final section.